Hi, today we're going to look at how to use integration to find area between two curves. So we already talked about how to use a definite integral to think about an area or a signed area between a function and the x-axis. And so here we're just going to kind of extend that idea to think about how to use integration to find area of a region between two curves. Alright, so as with any definite integral, when we think about what we're actually doing, there's some kind of partition involved here. So we're going to have a partition of, in this case, the interval of a to b. And so we're going to chop that up into little subintervals is what we mean. We're going to choose an x-coordinate in each of those subintervals. And remember before we called that c sub k in each of those subintervals. And then we're going to use the width of the subintervals and then the point, the x-coordinate we have, to get some heights here to build some rectangles. Alright, so we're thinking about partitioning up this interval from a to b. So we've got all these little regions here. We pick a point c sub k within each of those. And then what we're going to do is build rectangles that go basically from the top curve to the bottom curve. So we use that x equals c sub k to get a y coordinate on each of those curves. So we've got an f of c sub k on the f function curve and a g of c sub k on the g function curve. And then what we want to do is represent the area of that rectangle. So we're going to have one rectangle that I drew here, and that rectangle's area is going to have a height that goes from one y coordinate to the other. So we're just going to find the difference between those two y values here. So we're going to have f, the top one, f of c sub k minus g, the bottom one, g of c sub k. And so that's going to give you the height of that rectangle. That's true height. Since I took larger minus smaller, even though the g is negative, larger minus smaller, that gives the actual height. That would never be negative. Could be 0 if the f of c sub k and the g of c sub k were the same. But as long as I take the top function minus the bottom function, that difference would never be negative. And so that's height of the rectangle. And then when I want to take that times the width of the rectangle, which just like before when we had those widths of those rectangles, that width would be delta x sub k. Okay, so that represents height times width of one rectangle, and we can do that for all the rectangles in our partition. We can add them all up. We can take the limit as the norm of that partition approaches 0. And when we do that, we end up with, that's how we define a definite integral. And so we're going to have f of x, that's our top function, minus g of x, that's our bottom function. That part represents a true height of rectangles, and then times dx, which is what corresponds to our delta x. So I tried to write this kind of right below each other here, so you can kind of see how the elements of the definite integral correspond to what we have in the development there, where we were thinking about it in terms of a Riemann sum. And so we've got the integral from a to b. It would be important to remember that these are x values. We don't usually write x equals a and x equals b, but remember that those are x values. And this gives the actual area between those two curves, between f of x and g of x, so that shaded region from a to b. And that's actual area, so that should not ever be negative. So that's really what we're after here. There may be times where we have a region that looks a little bit different. I'm going to draw another little picture here at the bottom and talk about how sometimes we may want to do this problem a little differently. So depending on the shape of the curves, we may have some curves that look something like this, and we're interested in an area of a region between two curves that look like that. And so we can basically use the same idea of a partition and building rectangles, but we're going to do that in a slightly different way. So I'm going to scroll up here and just try to draw on that picture a little bit here and explain what we would do there. All right, so in a region like this, one issue is that the top function and bottom function are different on different parts of the region. But you might notice that if I just look at left function and right function and think about building my rectangles horizontally instead of vertically, we've got the same curve forming the left and right. So in a problem like this, we're actually going to partition a y interval. I'm going to label this A, but you could call it something else if you like, and y equals b there at the top. And so for a region like this, I could think about doing my partition in the y direction so that I have all these little intervals that have y sub k minus 1 to y sub k. Just like we did with partition in the x direction. So I'm partitioning that interval from A to B, but these are the little sub-intervals in my partition. And then we would choose a y value in each of those little sub-intervals. And in this case, though, the height of those rectangles would be delta y, and the width of the rectangles would be determined by those curves. So I'm going to name these curves. These would not be y as a function of x. Notice these two curves don't pass vertical line test, but they could be written as x as a function of y. So where I have that equation solved for x. And I'm going to call x equals f of y, this one that starts out on the left but then curves to the right, so that on our region it's on the right side. And then the other curve here, I'll call that x equals g of y. And so if I look at the width of that rectangle, that width would be my f of c sub k minus g of c sub k, but those c sub k values in this picture would be y values. So in this kind of picture, we can also get area by setting up an integral in terms of y. So our partition is all with thickness, or in this case height, delta y, so we're going to have a dy on the end of our integral, and then everything else in the integral is also going to be in terms of y. So my limits of integration would be those y values, and then my functions here that would define the width of the rectangle here are going to be in terms of y values, f of y minus g of y. So everything here in terms of y. So if I have dy at the end, then all of my function equations need to be given in terms of y, and my limits of integration need to be given in terms of y as well. I'm going to do a little bit more labeling on both of these just to make sure. Sometimes students don't think about the picture when they set this up, but it's really important that you think about the picture so that you get everything in the right order. On the dx integral that I have here, if you look at the picture, you notice that the f of x function that I have first here, that's the top function, and the g of x function is the bottom function. And because of subtraction, it's important that you get those in the right order. If you get them in the wrong order, then you'll get the wrong sign there. And your limits of integration, your x value here is at the left, the smaller value on the lower limit of integration, and then the larger value, which is going to be on the right, on your upper limit of integration. And for the dy integral, it's also important to think about the order here. So instead of left to right for your limits of integration, those are going to be top and bottom, but you want the lower one to be the smaller one. So in terms of y, this would be the bottom for our limit of integration. And then the biggest y value at the top would be our y equals b. And then the functions here represent the width of that rectangle. So this part here represents the width of the rectangle. And so we want larger minus smaller. So when we're thinking about width in left and right, larger is on the right side. So that would be the function that's on the right side of the region. And the g of y would be the function that's on the left side of the region. Okay, so we're going to look at a picture here and look at setting up an integral both with respect to x and with respect to y over this same region. Okay, so they tell us here in the problem that the two curves here are y equals x squared and y equals 2x, And so it's pretty easy to tell which one is which. We know y equals x squared is a parabola and y equals 2x is a line. We would want to know those intersection points so we can use those to set up our limits of integration. So there's a little grid here. It's pretty easy to just look at it and see the intersection points, but you also could use algebra to think about those intersection points. Okay, so if I want to set this one up using a dx integral first, then I would be thinking about partitioning along the x-axis. So my little rectangles would have width delta x for the dx integral, and then the height of those rectangles is going to go from the line to the parabola. So I'm just going to write some words here. We're going to have our x value at the left and our x value at the right, forming our limits of integration. And then when I think about the functions here, my height of my rectangle goes from the line to the parabola, top minus bottom. And then that's a dx integral. So this is not an okay way to set that up, but this is how you want to think about it. And then let's go ahead and fill in the values here. So at the left side of my region, my x value is 0. And at the right side of the region, my x value is 2. And then I need a dx integral, so I need these two function equations here given in terms of x. So my equation of the line, that is y equals 2x. And then the equation of the parabola, that's y equals x squared. All right, so there's that definite integral. It just asks us to set it up here and not evaluate it. But there's that integral set up that would give us the area of that shaded region between those two curves using a dx integral. All right, and then if I want to do the same problem but using a dy integral, I would be thinking about partitioning in the y direction. So I'd end up with these little thin rectangles that would go across the region. So my partition is in the y direction. So for that dy integral, we're going to let my y go from my lowest y value, so that would be at the bottom, to the highest y value, that would be at the top. And then I want to think about the width here and think about going largest to smallest on the width. So it's important to look at the picture to think about that. The width is from bigger to smaller. So that's going to be from the right side to the left side for the width of those rectangles for the dy integral. All right, so the right side here is the parabola and the left side is the line as a dy integral. I looked at the picture to decide what order that subtraction would be in. This one's on the right, the parabola, and the line is on the left. Okay, so I need to go ahead and set up my integral here. It's a dy integral, so everything needs to be in terms of y. So my limits of integration are y values. Y is going from 0 to 4. Be sure you grab the right coordinate of those points there, y values. I have a dy integral. So what I need next here is the equation of that parabola, but it needs to be in terms of y. Since I have a dy integral and my limits of integration are in terms of y, I need that equation of that parabola given in terms of y. So I'm going to need to go back up to my graph here and do a little bit of algebra to solve that equation for x. So when I solve that parabola for x, I technically get x equals plus or minus the square root of y. X equals the positive square root of y is going to be the part of the parabola where the x coordinates are positive. So that's the part we're actually on, the right half of the parabola. And x equals the negative square root of y is the part of the parabola where the x coordinates are negative, which would be the left half of the parabola. So we don't need that one for this part. So this x equals positive square root of y is the part of the parabola our region is on. And then, so that's what I'm going to have here for the parabola, square root of y minus. And then for the line, I also need to solve my equation for the line for x so that it is given in terms of y. So I'll just divide through by 2 or multiply by 1/2, and I'll get x equals 1/2 y. All right, so there is my integral set up as a dy integral. And since the area is the same, look at the picture, it's the same space. Whether I evaluate the one that's dx or I evaluate the one that's dy, I should get the same answer for both of those. If we don't, you did something wrong. Okay, we're going to look at one more quick little picture here and just think about a region like this. So this one is a region that I would definitely want to use a dx integral. to set this up. The dy integral wouldn't be great here because I have different boundaries in a lot of different parts of the region. But one important thing is that if I think about setting this up with little vertical rectangles, strip rectangles here, so that the width of my rectangles is delta x, one important thing to notice is that on one part of this region I have one function on top. It looks like I have a line and a parabola here, although I don't have equations. It's hard to tell for sure if that's a parabola or just some other curve. But on one part of the region, on the part that's on the right here, I have the line, the f of x function on top, and the parabola shaped graph, the g of x function on the bottom. But on the left side of the region, they're switched. So the parabola, the g of x function, is on top, and the line, the f of x equation, is on the bottom. So if I want to find the area for this whole region, I actually have to do this one as two separate integrals. So I'm going to set up one integral over the region on the left from x equals a to x equals b. In that region, the top function would be g of x, and the bottom function would be f of x. So top minus bottom on that left region. And don't forget your dx at the end, that's important. And so that's going to give me the area of this left region from x equals a to x equals b. And then I also am going to need to do a separate integral for the area of the right region and then add those two areas together to get the overall area. So for the right region, that goes from x equals b to x equals c. And on that part of the graph, my f of x function is on top and my g of x function is on bottom. Okay, and you should be saying, oh, don't forget the dx, right? Don't forget the dx there at the end. All right, so this picture is just intended to illustrate that there might be times where you have to split into separate integrals to find the total area. And we'll look at some examples in some of the videos where we actually calculate these and evaluate the integrals.